Zoom! New.
Hey yo! Okay, so this is our control panel mechanism. I'm going to give you a brief rundown. So we encountered an issue doing our spinner control panel mechanism. We wanted to fit in our frame perimeter but still hit the wheel, or the spinner I mean. The control panel sticks out just a little bit, and so we went for a passive mechanism. We're going to have it hinge out of this, but that was too complicated for us to do in the amount of time we had. So basically it's a passive height thing. It's attached to the non-moving section of our elevator. We just have a bracket so it wouldn't interfere with it. This is the correct height it needs to be at, so we just can run up to it. Squishy wheels, so you know there's a little give there, so we can kind of hit it, really make sure we're getting some traction. It should work.
So this is our hook. The idea behind it is to use this elevator to lift it up to the generator switch, and then we'll just drive up. It'll hook on and then lift off of the elevator like this, and then we have a winch back here to pull the string in. And then while we are on the generator switch, we have this wheel here to hopefully take us side to side so we can kind of try to make it level. And this gearbox here is 100-to-1, and then we have a 3-to-1 reduction here, so it's 300 gear ratio. We tested this on the bar, and it was able to move a person that was hanging from it, so I think it'll work.
Okay, so today we got our shooter installed and mounted with our encoders on each wheel to control speed, and we have it hard mounted, and we're going for 2 angles, an intake angle and a shooting angle with our pneumatics that we're using for this. We also got our energy cell storage here, which is just a sono tube covered in carbon fiber tape to reinforce it. And we're hoping that works to be able to suck in the balls and feed them up for storage. So today we got our electronics board mounted in a neatly fashioned in a good location. We're currently working on wiring the rest of the robot, and we have our pneumatics set up for our intake and our shooter here.
Oh, hey, didn't see you there. Hey, I'm Adam from Ri3D, the ZouKeepers. I'm going to be talking to you about our software. So for our software architecture, we decided to use a state machine. Basically what that is just a while loop, and it goes through a series of states inside of a case structure, and one by one we'll execute them every time that VI is run. So we have one in begin that will go through and initialize all of our components, like the joysticks, the drive, the flywheels, all the motors, compressors, that kind of stuff. We have another one in teleop that will go through, and this one's a little bit more complex. We have what we call a read, calculate, and write kind of structure. So first things, we read all the inputs, we calculate what all the outputs should be, and then finally we will write those outputs to motors, actuators, pneumatics, all that stuff. So for the begin state machine, we have all of our possible states here, and we keep this in an enum. Our while loop will go ahead and cycle through each of these and run whatever initial configuration we need. So we set up the joysticks, the drive, compressor, and then we have one for stop that will that's basically it. Nothing happens in stop, it just stops. So teleop state machine is a little bit more complicated. We go ahead and we have a read calculate and write structure to our enum that it cycles through. First thing that we do is we read the joysticks. So each of these sub-VIs has a standard input and output. This is a cluster that we call teleop local data. And so this makes it easy to delegate the code the code that we need written to the other programmers on the team. We keep that in our type def. And this basically has all the inputs and the outputs that's going to be passed through each of the states. And this state is carried over through a shift register in the while loop. This basically has the joystick inputs. It has all the outputs that are calculated during the calculate states. So for example, our drive, I'll just run through that example. We read the joystick first, and what we do here is we pull in the joystick, we get the values, and we have this sub-VI that will go through and turn the joystick output, which is an array for the axes and an array for the buttons, and we turn that into a nice little joystick cluster. So it's a little bit easier to work with, and we can pull out specific data that we want. And we push that into the new cluster, and that gets outputted and sent back into the main local data, and that gets put into the loop. After that, we will calculate the drive. Calculating the drive, we pull out the joystick values that we're interested in. Here we set a deadband limit in case they wiggle around so the robot isn't freaking out. Here we set a 75% or 25% cut from the rotational power, and then we output that to the outputs, which are drive forward and drive twist in the cluster, and that gets outputted into the teleop local data cluster and sent back through the loop. Then we go ahead and we write drive, and this takes in the local data again. It pulls out the drive forward and drive twist. It pulls out the motor ref num, and it tells it to drive. That's about it. It doesn't change any data, so the input is the same as the output, and that just keeps things kind of standardized. So it's easy to just go through and plug in these sub-VIs to the main loop. So something else that we did to kind of make things a little bit easier is whenever we had a lot of people working on this, sometimes people would get confused about the name of the ref nums because you just pass a string into the get ref num block. So we had kind of an interesting way to deal with that, where we have an enum for each of the possible components of the robot. And so that allows us to choose an enum, pass it into a convert to string block, and that will output just the enum name as a string. But that's standardized, so no one's accidentally typing it in wrong or something like that. It just kind of makes things a little bit easier, a little bit smoother when you're dealing with more people. Oh hey, and it's either. And I'm going to be talking a little bit about the Pixie 2. This is a cool little camera that we got from Andy Mark. It's got a bunch of cool features that make vision processing really easy, as opposed to doing it manually, either on the Rio or on a Raspberry Pi. So let's get into it. Several different profiles for objects that you'd like to track. It's relatively easy. You just point the camera at the object you'd like to track. You hold down the button on the camera for just a few seconds, and you let go, and it will go through and highlight different objects that it thinks that you want to track. In this case, the ball is the only one. Go through, press the button again, and it will go through and start tracking that object. We can go and roll it around, it can track it, and we're getting a consistent 61 frames per second on the object, or just on the feed in general, running through all this vision processing. We can track multiple objects, such as a red Solo cup. And the same process, just hold the button down, let go, and it will find the object that we want to track. So I'm gonna do it like this. Push the button again, and there it's got another object. So we see that it has highlighted both of these objects here. Whereas this is the first signature, the ball, and the second signature is the cup. We can go through into configure, and we can actually rename those. So I'm gonna call signature 1 ball. Crazy, right? Second one's gonna be called cup. Apply, and now it's highlighting those as a cup and as a ball. We put them near each other, still recognizes the difference. This is hue-based, so if they were the same color, it might have issues differentiating between the two of them, or it might see them both as the same object, or as two different versions of the same type of object. And you can configure all that stuff, like how many objects should be in the frame, how many objects should exist per profile. So you only get you can only set it to have only one, which is what I have here. The Pixie 2 also has a lamp that we can turn on, which kind of makes the hue, whenever you set the signature, a little bit more consistent for when it's running and all that, for if your robot goes in a different types of lighting. And you can configure all of this stuff on the RoboRio through LabVIEW SubVIs. In LabVIEW, you've got a few different ways to configure this Pixie. It connects to the Rio, and it can communicate over I2C, SPI, or UART. And it's got a few different configuration abilities. You can turn the lamp on and off. You can set the LED, set the camera brightness, figure out how many FPS you're getting, all that stuff that you'd want to do when you're controlling a camera. So that's what we're using the Pixie for, just some basic object recognition and tracking. It can do a few other cool things like line tracking, and it can also control servos. They have a cool video on their website of a little tank robot kind of looking at a ball and kind of following it around. Through LabVIEW, you can configure the camera, like the brightness, the different modes it's in, and it can communicate with the Rio over I2C, UART, and SPI. Okay, that was the Pixie 2. Thanks for taking the time to watch this video, and I'll see you guys